So my name is Shih-Chii Liu. I'm from the Institute of Neuroinformatics at University of Zurich and ETH Zurich, and I co-direct a census group together with Toby Delbrook, and we've been developing neuromorphic spiking sensors for the last 2 decades. And so today, in particular, I want to talk about neuromorphic audition for robotics. But before I do so, I want to thank the organizers of this unconventional sensors workshop for inviting me to give this talk. And so on the left here, oh wait, let me turn on my laser pointer.
So we cannot share. I cannot see at least your screen. Yeah.
Oh, sorry. Yes, thank you. Thank you for telling me this. Before I just kind of. Yeah. Can you see it now?
Yes, now it's perfect. Thank you.
Okay, perfect. Yeah, thanks. Let me first also get the laser pointer, so I'm ready to go. Yeah. So anyway, so this is the dynamic audio sensor that I'll be talking about today, along with a particular robotic platform. But the first thing is, why do we use neuromorphic sensors for robotics? And so most of you probably know about the dynamic vision sensor, where the camera responds to local temporal changes, contrast changes. And so if you have a rotating disc with a dot, and if you look at the output of a standard camera, then you're going to see a set of frames where it looks pretty redundant, except for where the dot is in a different spatial position for each frame. But if you look at the dynamic visual sensor output, then you're going to see this sparse stream of asynchronous spikes that come out from the camera, where they come from the pixels that see this moving dot. And so because of this asynchronous way of transmitting the events and also what the camera is looking for, we get minimum latencies in sub-milliseconds, and also the average data rate is reduced because the sensor is data-driven. And so the same thing applies to the dynamic audio sensor. So what you see here will be the output of the frequency channels of the cochlea as a function of time. And most of the time you don't see anything, but whenever someone speaks, then you're going to see a set of spikes that come out from the sensor, from the different channels that see the frequencies of the sound. Now, what we want to do is, of course, is to put the sensors on a robot platform. So this is a robot head that was built by Jörg Conrad at KTH Stockholm. And also we had tried putting on this Omni robot that he built. And so here you can also see the dynamic audio sensor board. And so I'll tell you a little bit about kind of the experiences that we had when we used the sensor. So the outline of the talk is as follows. So I'm going to talk first about the dynamic audio sensor and its operation. And then I'm going to talk about a set of event-driven DAS algorithms. So localization from DAS output, tracking a source from DAS and DVS mounted on a robot head. I also talk about speech recognition on the FPGA deep network accelerator that uses the DAS spikes, and finally the conclusion and the outlook. And so let me just start with the dynamic audio sensor itself. So just to give you an idea of what's on this sensor. So I start off by just describing quickly the operation of the biological cochlea, right? So the sounds coming in hits the eardrum, which causes the bones of the middle ear to vibrate, and the last bone pushes on the cochlea, which is shaped like a spiral. And if you go unroll it, then there's a membrane called the basilar membrane that sticks in the middle of this fluid chamber. And the membrane is shaped in a way so that it's narrow and thick at the beginning and thin and wide at the end. And so if you play a certain frequency sound coming in here, you'll see some place along the membrane where you're going to see the maximum displacement of the membrane. And so you can sweep a bunch of frequencies and then see at which place along the membrane would you see the maximum displacement. And this was done back in the 60s by Juan Becasey. And here you see the relative amplitude of the displacement as a function of the frequency, and also how the different places along the membrane, as you move away from the beginning of the membrane, changes depending on the frequency that it sees. So you can see that at the beginning, it likes high frequencies, and then at the end of the membrane, it likes low frequencies. So when you look at something like this, it looks like a filter. And so you can make an electronic model of a set of bandpass filters where, again, you set the preferred frequency for the range of frequencies that you see here for the biological cochlea, which is probably around 3 kilohertz down to about 100 hertz or so. And the input to the filters come from a pre-amplified output of the microphone. And I show you now the filter responses of our latest cochlea. And so what I plot here is the gain of the filter as a function of frequency. So there's 64 channels on the filter. And so you can see the nice matching between the different channels. And this is something that's quite difficult when you're doing analog circuit design to get this nice matching. So pretty happy with that. So now for each channel, in addition to the filter, we also added a model of the inner hair cells. So what I haven't shown here is there are a set of cells that sit here on the membrane that transduce the vibration of the fluid into electrical signal. And if you look at the functionality of the cells, it looks like a halfway rectifier. And so we built a halfway rectifier circuit here. And then there are the spiral ganglion cells that transmit the information out of the cochlea, and they transmit them in the form of spikes. And so here we model it by integrating fire neuron. And so for the 64 channels over here, you would get these asynchronous spikes coming out from the channels. And we transmit this using the AER protocol, which is the address event protocol used on all our sensors. And so the nice thing about implementing them on silicon is you can implement it in a very small area. So this is a binaural cochlea, so we have 2 ears. And you can see that it's in an area of about 6 by 4 square millimeter. You can package it up. So here it is sitting in a printed circuit board that holds a bunch of electronics, which we need to interface to the computer. And then the input to the cochlea or the DAS is connected to the 2 microphones. And so just chip responses from this DAS chip. So here you see the blocks of the channel again. So you've seen this already in the previous slide, right? So this is the output of the filters. And then what I want to show here are the spiking responses that come out from the end of the channel. So here we have the 64 channels, and we're going to play a chirp, which is a sound that now goes from 6 hertz to 21 kilohertz over a time of more than a minute. And then what you see here are a band of frequencies that respond when they see the frequency within their filter response. And you can see a nice band of channels that respond to the changing frequencies. And for this particular cochlea, which is 2 by 64 filter channels with a frequency response that goes from 20 hertz to about 20 kilohertz, we get about 1 kilobyte of data rate. And it burns only about 55 microwatts for the analog core power. So basically for the blocks that you see up to here. And now I show you some spiking responses. So the first one you've seen before, right? So now you see when someone says a sentence, so here are the 64 channels, you see the spike response, and then I can show you another view of it where now time is the third dimension going to the board or the screen. Yeah, so you see the stream of spikes that roll by as soon as you hear a sound. And now you can you can ask if the spikes represent the original analog input faithfully. And so what you can do is you can take a sentence, for example, she had your dark suit in greasy wash water all year round. And then you can compute the spectrogram. So basically you look for the power in the different frequency bands as a function of the words in the sentence. And then you can see these different patterns that appear, of course, for the different words. And also, for example, the harmonic stacks down here at the bottom. And now what I do is I take the spikes, I take the sentence, I play it to the cochlea, I take the spikes, I bend them. And so this forms the cochleogram. And now again, for the different words, you see different bands that show up. And these patterns look very similar to the spectrogram. And so another way of testing whether you can still get back the original sound is that I'm going to first play the original audio. And now I'm going to take the spikes and I'm going to reconstruct the sound. Yeah, so you can hear it comes close to what the original sound sounds like.
Shih-Chii, I think we don't hear the sound from
you don't? This is what I was afraid of. All right, so let's see if this goes.
She had your dark suit and greasy wash water all year.
Can you hear it?
Yeah.
Yes.
Oh, wow, lovely. Thank you, whoever that was, to get the hint. Okay, and then here's the reconstructed sound.
She had your dark suit and greasy wash water all year.
Okay, all right, great. Okay, so next I talk about some of the event-driven DAS algorithms that we've developed. So we're going to go through the localization algorithm, tracking the sound source, and then the speech recognition algorithm. Now, so one way of determining where a sound source is in space is by using interaural time difference, or ITD. So depending on where the sound source is, and the time taken for the sound to reach the left and the right ear is different, right? So if it's in the center, this delta t will be 0. If you're off to the side, it's going to be negative, some value, and on the other side be positive. And so what we want to do is to now take the stream of spikes that you see from the two cochleas, and then to determine or to estimate what this delta t is. And so the way that we do it is from a stream of events, we extract an ITD for each event. And from every event, where the event consists of the timestamp, the frequency channel from where it comes from, and also the ear, what you do is you get the nearest event from the second ear in the same frequency channel, and then takes its timestamp. And then what you do then is you compute the ITD, which is really the first minus the second timestamp. So in this example that I have here, where you have 3 events from the left ear and 3 events from the right ear, then you can see the ITD here will be 2, 1, and -3. Right, and so what you do next is that you compute the histogram of ITD. So here I show a histogram going from -700 microseconds, which is kind of towards the left extreme of what the ITD is for the spacing between our ears, and 700 microseconds on the other side. And for every ITD that we get, we weigh by the interspike interval before the last spike. So which means that depending on the time between the 2 spikes in the same channel, if there's a big pause before the spike arrives, then we weigh it heavier. And then we throw that into this histogram. So in this case here, since we have 3 ITDs, you can see 3 entries into the corresponding bins. And then the next thing is that we decay, of course, the histogram exponentially over time. And then this is an algorithm that Holger Finger worked on back in 2016. And so I'm going to show a video of him where he ran the algorithm on a laptop. And so the sensors, if you can see it, so there's a DVS and 2 microphones sitting on top of this ventil unit.
Here we see a robotic head with retina and cochlea, which works only with spikes. And here on the screen we see the picture from the retina. Here we see the spikes from the cochlea and a localization result showing the peak where the sound is located. With this, the pan-tilt unit is driven such that it orients towards movements in the visual field and towards localized sound.
And so if I now start talking, let's see if it moves towards me, and yes, it does.
And now I will start talking, and now it moves back where I am.
Now.
Okay, all right, so you get the idea. Okay, and so then we decided to make a more sophisticated robot head. So this was done by students in Jörg Conrad's group. And so it has a neck, so you can do a pen and a tilt. So you can look for the azimuth and also the altitude. And so the same thing for the 2 DVSs. So they also have their own pen tilt system, right? So like your eyes. And then we have the microphones, which go to the Cochlea board, which you don't see here. And then a microcontroller board, of course, that controls the motors of this robot head. And so what I want to show next now is a video from this particular robot. So what you see here will be the DVS output from the 2 DVSs, and you're going to see that they vibrate because we wanted to get an idea of what the scene is, so we vibrate the DVS. And then here is a larger picture of what's going on, because you can pan also the neck. You can turn the neck. That means you can see a much bigger field of view than just what the DVS sees.
Here you can see the robot head with the 2 DVS cameras and the 2 microphones on its sides. The jittering motion of the cameras is clearly visible. Each of the cameras is connected with a USB connector to the PC. The 2 microphones are hooked up to the Cochlea AMS1B board. The computer controls the robot head with this PCB and 2 microcontrollers. As you can see now, the head moves as long as I'm speaking within my direction and tries to track my movements. Here you can see how the head orientates itself towards me and paints its picture.
Okay. So now we wanted to quantify how well you can actually localize somebody. And so we went to now a recording setup where we have a set of speakers, right? So this in a room at the University Hospital. And then we put the cochlea in the middle of this circle of speakers. And so we did recordings of a speaker at different speaker locations. The sound segments come from an audiobook or switchboard data set. So I play a sentence here so you have an idea of the audio.
Made the sheet fast and reached under the stern for the club. It was an oar handle from...
Okay. And then we did recordings under 3 conditions: clean, where there's one active speaker in a clean environment; noisy, when there's one active speaker with babble noise background; and conversation, where there are 2 active speakers in a conversation with non-overlapping segments. And to do the localization now, we use a different model. So we use a Bayes filter. And just to set the whole thing up, so now you can see the 10 speakers, right? The 2 microphones of the cochlea. And what we want to do is to estimate where the sound source is coming from, one of these 10 positions. And so for this, we use a hidden Markov model. And so here you see the states of the HMM and also the observations. And so in this case, it's the ITDs. And so we do a probabilistic estimation of the hidden states using the hidden Markov model, and we estimate the states, which are the locations of the speaker, from the observations, which are the ITDs. Okay, so for this then we have to compute the posterior, and the posterior would be the probability that the person is in a particular state, depending on the event K that you get, and then also on the ITDs that you estimate from all the K events that came before. And that's proportional to the prior and also multiplied by the likelihood. Okay, and so the likelihood can be estimated as follows. So basically you integrate the probability of transitioning from the previous state to the current state, and also the probability of the previous state depending on all the ITDs that you get from the last K events, okay? So now what we need to do is to estimate the prior, right? So the probability that you see a particular ITD, given that the sound source is coming from a particular state or particular location. And so we can do this by playing the sound source from all of the 10 positions, right? And estimating the ITD using the events of the cochlea, and this is what we show here. So these are the 10 positions. Each color corresponds to a different position, and you can see that it pretty much looks a bit like a Gaussian, yeah. And so we have the prior, and from that we can estimate then where the position of a sound source is when we get new events from the cochlea. And so here's an experiment with changing positions of the speaker. So what we do now is we code the speakers by the angle, right? So here's 0 degrees, and what we're going to do is we're going to move the speaker from 0 to 90, and then counterclockwise back to -90, and then back to 0. And so what you see here in the plot, which is now for a male speaker in a cleaner environment and where we have the ground truth, right? So what you see first are the horizontal lines. We show you the ground truth, where the speaker was speaking. And then in yellow are the estimates using the Bayes filter. And so you can see that it corresponds quite well to the location of the ground truth. Of course, you do see mistakes. For example, you see them here and a little bit here, right? But overall, you can see that it tracks quite well where the sound source is. And then we do the same thing for the female in a clean environment, and we found that, yeah, it tracks pretty well also where the sound source is, but then you do see more mistakes, right? And so we can quantify this. And I just show you a subset of what we got in this particular experiment. The details are in a paper. And so for the 2 cases here where you have the male and the female in a clean environment, the accuracy per event was 93.8%, and that for the female was 81.7%. But the nice thing is that this average prediction lag, so the time that you need to estimate where the position is from an event is about 7 milliseconds for the male and 12 for the female. And so in general, what we can conclude is that at least for this set of recordings, that there was better accuracy on the male speakers than on the female speakers, and that's partially due to the events that we get from the different frequency channels, right? So it's actually more variable when you get from the higher frequency channels, right? And also the lag on if you compare what we got here for the prediction lag and you compare it with the lag on the sample microphone data, that would be about 100 milliseconds, so it'd be much longer. So now I turn next and talk about how we're now using an event-driven audio system, which together with deep networks, and also together with the DAS spikes. And so the pipeline looks as follows. So we have the sound coming in again to the DAS, produces spikes. And what we're going to do is we're going to create frames of feature frames that we're going to use to drive an event-driven deep network. And so this is the work of Chen Gao. And so the event-driven deep network that we use for the speech applications are recurrent neural networks. And it's event-driven because if you don't get an input frame, then we don't time-step the network. So basically, we don't compute the network when we don't get any input frames, or the input frames are zeros. And so how do we create an input frame? So here's just one example. So if I get spikes from 2 different channels, then what I can do is I can create a constant time bin frame. And so from the 2 channels here, what you would get for this 4 frames that I show here is for the first frame, I get 2 spikes and then 1 spike in that particular time. And then from here, we get 1 and 3 spikes. Here we get 3 and 2 and 2 and 2. And so now we feed these frames into the network as we get the spikes. And if there are no spikes here, then you would get 0, 0, and then you wouldn't compute this network. And so now I'm going to show an example of how we use this whole pipeline on a speech recognition task. So this is a continuous speech recognition where we're going to recognize digits, single digits, like 0, 1, 2, 3, 4, 5, up to 9. And this particular network also has been implemented in FPGA. So you're going to see a demonstration video of how it works.
This is the setup of our spoken digit recognition demo using the Cochlea board and our Delta RNN accelerator. So this board is the Cochlea board that is used to convert a microphone signal to spike events. And events is sent from the board to the computer using a USB cable. As you can see, in the left window, you can see the plot of all the events. So the horizontal axis is the time axis, and the vertical axis is the channel axis. There are totally 64 channels, and each channel corresponds to a bandpass filter. The spike events also goes from the Cochlea board to an FPGA board through a cable that transmits the spike events in the AER protocol. On this FPGA board, we implemented our Delta RNN accelerator that is able to run a gated recurrent unit-based recurrent neural network to do the spoken digit recognition. And the recognized digits will show on this plot. So we have totally 12 labels, and the vertical axis shows the probability of the recognized digits. Now let me show you how the demo works. One, 2, 3, 4, 5, 6, 7, 8, 9, 0, 0, 0, 5, 6, 6, 7, 6, 5.
Okay, all right. So you can see it's actually quite tough with the 6 because the network has been trained on this TI digit data set, and then there are not a whole lot of accents coming from Asians. So the 6 is quite difficult. Yeah, so okay, to conclude, an outlook. Right, so hopefully what you can see from the set of examples that I showed, that event-driven processing can save at least 10x of unnecessary computes, and therefore the energy consumption of a system using an event-driven sensor. By using the DAS, the latency for inferring a spatial location is shorter. It's around 10 milliseconds versus 100 milliseconds. And for the DAS digit recognition system, the number of computes for generating the event features is lower than that for the sample audio. So I didn't show this, but we can generate this constant time features every 5 milliseconds instead of 20 milliseconds for MFCCs from sample audio. So our outlook is to finish building this quiet robot platform where the robot doesn't make any sound. So if you have a platform that makes sounds, then that's going to interfere with the spikes coming from the cochlea. And so this is a robot called a silent runner, where it moves extremely fast but doesn't make any sound. And we're also building event-driven deep networks for the DAS and other audio tasks, including keyword spotting and speaker verification. So that was in the paper last year by one of the students. And finally is that we want to implement these networks running on the onboard FPGA of the robot platform so that we can show even cooler demos. And finally, I'd like to thank the students who worked on the project, Ineas Ciolini, Jitendra Anamula, and Adrian Huber, who helped with the recordings and also with the work on the localization using the base filter, Toby, who co-directs the group, Ilya Kizelev, who's working on the robot platform, and then Chen Gao, who did the speech recognition work. Okay, and then I'd like to thank also the funding agencies, and also if you are interested in what we do, here's our website link, and also thanks to all of you for your attention.
Okay, thank you very much, Professor Liu. Very interesting work. So does any of you have any questions? I am reading already the first one in the chat. So Cyber Fidelity is asking, what microcontrollers did you use in your work?
What controllers?
What microcontrollers? Yeah.
Oh, so this is the one for the robot head?
So yeah, so the one that asks these questions, Cyber Fidelity, can you be more explicit, or maybe
yeah, so,
you can plug your microphone and maybe ask yourself? Both robots, it says in the chat.
Oh, for the robot head. Yeah, so the Pentium unit, the first one, that was a commercial system that we had. So you can, I forgot the name of the model now because it's quite a while ago. It's just I think it's just a simple microcontroller. I don't remember the model because it was done a few years back, but it's not any fancy microcontroller.
Mm-hmm. Okay.
Unless you want to be more specific about what the specifications are of that microcontroller.
So it says in the chat, in continuous speech recognition, did you try with another voice with a different accent or pitch and compare it to original voice? Was there a noticeable difference?
So this is the reconstructed audio or the digit recognition?
Continuous speech recognition, it says. So I suppose.
Oh yes, right. So
yeah.
Okay, right. So in the demo, yeah, if you try it with my voice, then actually it does quite well with my voice, right? And yeah. So I think for the network to work much better, you know, it's like the training for the deep networks. You have to train it with samples from all the possible people that you might encounter, right? And so since we use the TI digit data set, it didn't have the representation of all the different people from a lot of different cultures, right? But it's very good on people that come from the US and also from Germany, for example. So if we were to redo the training, we would have to collect a much bigger data set of people from different countries.
Okay. Yeah, Toby Delbrook is saying in the chat, it was trained on T digits, recorded with Cochlea, also augmented with noise samples. Yeah.
Yes. Yeah, I mean, so collecting data sets is actually quite difficult, right? Because in this case, to train the network, we actually have to play the data set out to speakers and then collect the spikes from the data set, right? So we couldn't just take say the TI digits data set and then start training the network, right? So we actually have to get the actual spikes. And so that That took us, I think, over a week just to get the data.
Okay. Okay, yeah, but it's only a matter of data, right? In principle, there is nothing that prevents to recognize, different accents or pitch, right?
No. Yeah.
Okay, any other question?
I have maybe a quick related question. So if you compare the recognition performance of the whole setup to the best in the state of the art, it's probably kind of not quite there yet.
Yes.
So the question would be, what is the main bottleneck there? Is it really the data, which is not so vast as others can afford, the large companies can afford, or is it maybe the sensor or the network? So what are the challenges?
Yeah, right. So that's a very good question. Yeah, so the output of the DAS, so we've done a lot of comparisons between the output of the DAS and also just the conventional way of generating features. And because the DAS produces the output as spikes, so you've actually done a little, some decision, right, when you transmit the information. And so if you want to do a simpler tasks like voice activity detection, keyword spotting, what else, localization, then the output of the DAS is great. But if you want to do something like natural language processing, like recognizing, a whole data set of words, like 1,000 words, then you're not going to beat the conventional way of generating features, because there you keep all the information, right, in the spectrograms. But with the DAS, you're actually making decisions, because when you create a spike, it's non-linear operation. So you're actually deciding, when to generate the event.
Okay, so it's not quite lossless, right? So you said
no, it's definitely, not quite lossless. No. Yeah. So especially if you want the output to be sparse. I mean, there are ways to get like events that are more informative. For example, you can do this delta signal kind of way of transmitting the events, right? Because that's a way that people use to do analog to digital conversion, right? And then you can get also binary events, but then the density of these events will be much higher than if you had generated the events using this Cochlea model. So it's a little bit of this trade-off that we're looking for. And so we envision that this whole system would be useful for edge computing, like where you're going to do much simpler tasks than recognizing a whole sentence. So you would wake up, say, when you hear somebody speaking in the room, and then you would transmit, and then you would look for a keyword, right? And then once you hear the keyword or you recognize the keyword, then you would then turn on the actual more complex pipeline, right? Where you would now take the frames and generate the MFCCs and then transmit, all that stuff up to the cloud.
Makes sense. That makes sense.
Okay.
Yeah, great question, Julia. Yeah.
Thank you again, Professor Liu, for your answers and your very interesting work.
Okay, thank you. Thank you, Javier, and thank you, everybody.